Hello and welcome. Today, we are cracking the code on a family of chemicals that are, believe it or not, everywhere, from the deepest oceans to the highest reaches of our atmosphere. They're called alkyl halides. And you know what? They are way more interesting than they sound. So let's just start with a little puzzle. What on earth could possibly connect a fiery volcano, your morning cup of decaf coffee, and the delicate ozone layer that protects all of us? Well, the answer is a single group of molecules, and we're about to get to know them. All right, let's jump right in and start with the absolute basics, the fundamental building blocks of these molecules. So what is an alkyl halide? Well, put simply, it's a molecule built on a carbon framework. That's the organic part. Just picture a carbon atom, right? And usually it's holding on to hydrogen atoms. But in an alkyl halide, one of those spots gets taken over by a special kind of atom called a halogen. Fluorine, chlorine, bromine, or iodine. Okay, but not all alkyl halides are created equal. We actually classify them based on their neighborhood. Just look at the carbon atom that's directly attached to the halogen. If that carbon is bonded to only one other carbon, we call it primary. If it's attached to two other carbons, it's secondary. And if it's holding on to three other carbons, yep, you got it, it's tertiary. And this isn't just for fun. This classification actually makes a huge difference in how these molecules react. So now that we know what they are, let's learn how to speak their language. I know, naming chemical compounds can seem a little intimidating, but trust me, it's really just a set of rules. Once you know them, it's like you've cracked a secret code. The first rule, the golden rule, is super simple. All you do is take the name of the halogen, like chlorine, you drop that "ene" at the end, and you swap it with an O. So chlorine becomes chloro, bromine becomes bromo. You get the idea. Easy, right? Okay, here's the four-step game plan. First up, find the longest continuous chain of carbon atoms that has the halogen hanging off of it. That's your parent chain. Step 2, you've got to number the carbons in that chain, but you start from the end that's closest to the first thing attached to it, what we call a substituent. Third, you name and number every single substituent. And finally, you put all those names in alphabetical order right before the name of the parent chain. So let's actually see how this works with a real example. Here we go. The longest chain has 7 carbons, so its last name is heptene. Now we're going to start numbering from the right side because that gets us to the chloro group faster, putting it on carbon number 2. See that? We also have another little group, a methyl group, on carbon number 5. Alphabetically, C for chloro comes before M for methyl. So you put it all together and bam, 2-chloro, 5-methylheptane. It's a perfect, logical name that tells you exactly what the molecule looks like. But here's the thing. Understanding this chemistry isn't just some abstract exercise. As we're about to see, one particular type of alkyl halide had consequences that literally changed the planet. Let's talk about chlorofluorocarbons, or CFCs. You might know them by their brand name Freons. And for a long time, these things seemed like an absolute miracle of modern chemistry. They were incredibly stable, totally non-toxic, just perfect for using in refrigerators, AC units, and even as the propellant in aerosol cans. I mean, what could possibly go wrong? Well, it turns out their greatest strength, that incredible stability, was also their greatest, most devastating flaw. This slide really tells the whole dramatic story. Because CFCs are so stable and they don't dissolve in water, they don't get washed out of the air by rain. Instead, they just drift all the way up into the stratosphere. And up there, the intense ultraviolet sunlight is strong enough to break them apart, releasing these super reactive chlorine atoms. These atoms then act like little Pac-Men, just tearing through ozone molecules, turning them into regular oxygen and chewing a hole in our planet's protective shield. So let's wrap this up and go over the key things we've learned today. We started with the very basics, right? Alkyl halides are just carbon chains with a halogen attached. We learned the simple, logical rules to name them, turning these complex-looking structures into a clear, understandable code. And then we connected all of that to the real world with the story of CFCs, compounds that were celebrated for their stability, the exact property that let them drift into the upper atmosphere and cause a global crisis. You know, through global cooperation, we actually managed to phase out CFCs and address the hole in the ozone layer. It's one of the great environmental success stories. But it leaves us with a really critical question to think about. What miracle substance that we rely on so heavily today might be hiding an unforeseen cost for tomorrow?